good morning, everyone, and welcome. Thanks for waking up early to attend this talk on Unity's probe lighting workflows. In this fairly packed presentation, we are going to take a look at how to use Unity 6 features to create stunning and believable lighting for your world. But let's run through the agenda first. So first, we're going to start by a brief history of probe lighting techniques in Unity. Then we're going to show live demos on how to set up adaptive probe volume in your project, and also fix some common problems such as light leaking, for example. And then finally, we'll have a look on how to add dynamism to those projects using those tools. But first, some introduction. So this is me. I'm a technical artist at Unity. I joined Unity like 5 years ago. I have more or less 15 years of experience using Unities in multiple industries. And as an artist, sometimes as an engineer, sometimes as a project manager. And with me, I have two of my colleagues.
Hello, I'm Maxime, so I'm a technical artist for rendering and lighting. I joined Unity a little more than 2 years ago, and before that I was working on a lot of indie games for 6 years. And now, David?
Yeah, I'm David. Been working in computer graphics now for 2 decades, which is kind of scary. Since my first job as an architectural visualizer, I've had a couple of different roles. I've worked as an art director at Unity. I've been a technical artist embedded within R&D. And currently I'm working as a product designer, covering the area of lighting and graphics in general. So before we get into Maxime's practical demos, I just want to take a moment to give a brief history of the probe lighting workflows that we've had in Unity. But we'll start with a pop quiz. So would anyone in the room like to guess when light probes first appeared in the product? Unity 1? No, it was a bit later than that. 2012 was the first public mention of light probes that I've been able to find. That was Robert Chupid's GDC presentation, but actually it appeared in the code base even earlier than that. If we look at the commit history, it turns out the probes were first landed in Unity in 3.5, so that's 2011. So they've been around for a really long time now. Knowing that, maybe let's do a little recap on some of the workflows that we've tried to get away from. So classically, scenes would have been lit with a combination of light maps and light probes being placed by hand before we compute the tetrahedral holes, which enables us to do the blending. For light maps, light map UVs are generated at import time, and instances packed into seed-wide atlases and assigned coordinates. Light map texels are then sampled using path tracing, and the results are baked into corresponding textures. But of course, these are old techniques now. They've been in the industry for a really long time, and we've learned some stuff. So some of the things we're trying to get away from, probably principally that the iteration time was undeniably terrible. Light probes need to be meticulously placed by hand to get good sampling of the local lighting conditions, and that's super hard to do well. It requires lots of experience. Changing the scene geometry while iterating means that these laboriously placed probes have to be manually repositioned on each iteration cycle. Unhappy artists. Furthermore, the resulting spherical harmonic coefficients, which is our probe lighting data, is stored in a monolithic lighting data asset. Loading and unloading this data is really hard to manage, with no true support for streaming beyond the additive loading of these giant blobs of data. On the other hand, light maps, they have their own problems. So for example, they're unsuited to many geometry types, and especially foliage. If we look at the images on the screen here, can you imagine the surface area posed by this level of foliage detail? Imagine having to do the UV unwraps for all of these different mesh variants. Lighting continuity is really challenging to get right. Different parts of the scene use different lighting techniques, and that means it's very hard to get objects to feel plausibly integrated. Dynamic elements can feel separate. And just before I round out, just a few more considerations when we talk about light maps. They scale in world space. Given the surface area can cover the entire scene, the number of texels that need to be sampled grows dramatically, while the on-screen result actually could be quite small. And other disadvantages associated with being static are that light maps are storing a snapshot of the current state of the scene. Moving geometry is not reflected in the changing lighting conditions. Rémi.
So yeah, In Unity 2022, so more or less two years ago, we first released adaptive prop volume, or APV for short, in an experimental state. It was basically a successor to the light probe groups and light maps combination techniques, and it was solving most problems we had with them. In Unity 6, the features have reached maturity and is now the preferred choice for most projects. So let's start to see why. So the biggest thing APV has to offer is faster iteration time. And this is the key in most projects because it means a more polished product in the end. So the first thing it does better is that it's a unified system, basically replacing the combination of light maps and light probe groups and allowing you to light an entire scene with only one system. And the cool thing is that it's not just meshes that will benefit from this. For example, volumetric fog or even visual effects on all sample APV to have a better unified end project. Secondly, density and placement of the probe are handled automatically by the system, meaning you can spend way more time fine-tuning instead of placing individual probe or unwrapping UV, for example, for light maps. And if your scene change, for example, you just need to rebake, and then all of the probes and the density will actually follow the change in your scene. And you don't even have to worry about the time it takes to rebake, because for similar visual quality than light maps, it's way faster to bake. In addition, APV offers more built-in tools, and I'll try to go fast on those because Maxime will show you a live demo after. The first one is lighting scenario, basically offer the possibility to blend between two data sets. We also have sky occlusion, which basically bake occlusion data, and then you can multiply this occlusion by an animated sky color, for example. If you have a very large world, APV supports streaming by default, so that you can manage more easily your budget, for example. Also, since it's more efficient, APV has a way lower memory footprint when compared to Lightmap for the similar results. And I'll let David expand more on those numbers.
Yeah, so this is the Oasis scene that we've shipped with Unity 6 as the ULP template. If we take the scene and we do some very basic setup, we can see some quite drastic differences in the memory usage for the scene. With practically no visual difference, maybe even arguably an improvement in visual quality, we can see that the probe lit scene is around 1/3 of the size of the light map scene. And it's worth also mentioning that that size, 9.5 megabytes, is only paid once. That's the probe positions and the indirection textures. Additional lighting scenarios then are only a further 5 megabytes. So you can get many variants on the scene lighting for very little extra cost.
But then, David, I said that APV is so much better than light probe groups, then why do we still keep them in Unity?
Yeah, it's an obvious question. Clearly, Unity has decided to keep tetrahedral probes around, so there must be a reason for that. And the short answer is that they're very cheap. Unity supports a very broad range of hardware platforms, and we have users that are developing for very low-power devices, such as wearables, and legacy hardware that's still popular in developing markets. So tetrahedral light probes put lower demands on things like texture sampling and other hardware requirements, such as compute support. And for those reasons, primarily, they do live on in the product. Okay, so that's the history lesson. Let's go over to Maxime for the practical demo.
Yes, so this is the Oasis scene from the URP sample. And let's see how we can set up APV in this scene. So first, let's take a look. And this scene is using light maps. You can see that with this debug view. So basically, texels baked into textures. And it's also using light probe groups. So let's use the light explorer to find them. Light probe like this. And all right. Basically, you can see them. And those light probes are placed by hand. So basically, if you can use this tool, you need to move them. And it can be very time-consuming. And if you create a new one like this, let's see where it is. It's basically 8 probes that you need to place. So it can be hard to know exactly where to place them. And it can take a lot of time. So let's go back to the main scene. Let's see what we can do if we want to use APV and how fast it can be. So to set up IPV, let's go into the project settings, and I'll go into the SRP asset, and then I can switch from light prop groups to adaptive prop volume. And then in the lighting window, so rendering lighting, it's there. You can see this adaptive prop volume tab, and basically that's all the general settings for prop volume. And since light probe will be placed automatically, you need to set up the min and max distance between probes. So for example, from 1 meter up to 81 meters for this scene. And then APV is a volume-based workflow, so all you need to do is to create an adaptive prop volume like this. Let's place it there. As with the rendering debugger, so that's in analysis rendering debugger, we can use the prop volume section, and we can use the live update. So this way you can see the bricks of prop that will be generated, so you don't need to bake it to see it. And if you move the volume, it's updating in real time. And if you look at the right corner, you can see the different colors. So we have multiple bricks. The purple one is as a distance of 1 meter between probes. And you have also bigger bricks up to 81 meters between probes. So it's only generating probe inside your volume, and the closer to the geometry you get, the smaller bricks with more resolution, and then the further away, the bigger bricks. So we can place our bricks. For example, this is the main area where the player can walk. So let's place a brick volume there and generate some probes in there. Like this, all right. So for this area, even if we created a lot of subdivision level from 1 meter to 81 meters between probes, we can override this, and maybe we don't need a lot of probes here because this is the exterior and there is not a lot of complex indirect lighting. So this will be fine. Let's maybe rename this. So it will be main area like this. And we can create another one. Let's zoom on the tent. Light, adaptive prop volume. Here, right. So for the tent, I want a bit more resolution because it will be an interior, so the indirect lighting will be much more important. So let's use the full range from 1 meter to 81 meters. And let's place it like here, for example. Right. And this should be good for the tent. And last one for the background. So this one, we can make it global to affect the whole scene like this. And same, we can override the prop spacing. Maybe 27 meters will be fine. So yeah, you can see that we just have bigger bricks for the background. And then, so currently all the mesh renderers are still using light maps. We can see that with the contributor receiver debug view. Most of the mesh renderers are green, so light maps. So let's just convert everything to light props to see how it works, even with static objects. So let's select everything. Light probe, like this. All right, so everything should be good. Let's just generate lighting. So while it's baking, let's quickly summarize. By default, APV automatically adjusts the number of probes based on the proximity of the geometry. So this is based on the multiple subdivision level that you created. So if this is close to the geometry, you will use smaller bricks like 1 meter between probes, and further away, bigger bricks. But you still have some control, and you can create different areas with different volumes, like we did, if you want some areas to have more resolution, for example, the tent. And from a technical perspective, all those multiple volumes will be merged into a single structure at the end. So feel free to create as many volumes as you want, if you want a lot of control over the probe placement. So this is done. It was like 30 seconds to bake. Let's display the probes and see all the subdivision. And you can see that as we requested, we have a lot of probe for the tent, a bit more for the main area and a bit less for the main area and just a few for the background. So we can look at the lighting debug view. So for example, lighting with normal maps. And we have baked indirect lighting using light probe for the scene. It's already looking great. But if we look inside the tent, we can see that we have a lot of light leaking. Basically, the walls are really thin, so we can see the light from the exterior, the bright light, just leaking inside. So we'll see in a minute how we can fix that. But first, let's turn to David to talk about the design choices that we made for APV.
Yeah, I wanted to take a few minutes just to talk about some of the decisions that we made when we were designing the adaptive probe volume system. When we considered how we optimized the system design, it's important to think about reach. While we support most of the available platform range, the majority of our users are actually developing for mobile. We wanted to make sure that we were fully supporting this core group, and we definitely didn't want to build something that was only suited to high-end rendering on high-end devices. With that in mind, we've designed APV from the ground up to be about scalability. It enables scene-wide probe lighting on low-tier mobile with support for blended lighting scenarios and dynamic sky relighting. And it's actually surprisingly hard to pull that off. We provided that reach by utilizing great texture compression on disk and at runtime through technologies like optional vertex sampling of the probe data. But enabling this platform reach has imposed some technical constraints, and the most significant of that being the need to pre-compute the probe positions at edit time. But this is the unfortunate cost of speed. Before we go back to Maxime, I also just wanted to talk a little bit about user experience. Unity targets an incredibly broad range of development personas in the industry, from hobbyists to enterprise professionals. We've got customers that are using Unity all the way from student and early career to seasoned power users. And to meet their needs, APV needs to be both easy to use while remaining featureful and deeply tunable. So to those ends, progressive disclosure of complexity became a key design pillar when we thought about the workflows for APV. In the simplest case, we offer beginners a one-click setup. You just click Generate Lighting, and you get some plausible results. And for many users, that's going to be enough. But at the higher end, professional users need to be able to highly polish and optimize the results that they get using tools with fine local control. So talking about fine-tuning, it's going to be back over to Maxime to continue the demo.
Yes, thanks, David. So, as you said, it can be quite simple to set up APV for the first time, only a few clicks, and for example, for the exterior and for dynamic objects, it would work already great. But for static objects, especially for complex cases like thin walls and stuff like that, we need to adjust a few things. So let's see how we can solve this problem. So first, we need to understand what's going on. So in the rendering debugger, you can see there is this probe debug sampling debug view. And you can select a pixel and see which probe it's sampling. So for example, here we can see that it's sampling the interior probes, so that's great, but also the exterior probes. And this is why we get this leaking, because it's interpolated between those bright exterior probe and those dark interior one. So let's see if we can do something for this. First, we can try to add a volume and see if we can tune some of the setup for APV. So let's create one, and let's override the probe volume options. So the first thing that we can play with is the normal bias, and it's basically pushing the sampling location along the normal, so away from the wall in this case. And we also have the view bias, pushing it towards the camera. So it can be quite useful for fine-tuning, but I want to show you other methods to solve leaking, so I'll keep those quite low for this demo. Something like this. So since we have this clear distinction between the two areas, the interior and the exterior, let's see if we can split the scene for APV and giving instruction to where to sample for both interior and exterior. So the idea is to use rendering layer for this. So let's go into the project settings, tag and layer, and rendering layer. And you can create a new layer just like this. And I already created an interior layer and an exterior one. So let's just assign this to the objects. So the interior of the tent will be on the interior layer. And to see what I'm doing, I can use the rendering layer mask debug view with the interior and exterior layer like this. And we can do the opposite for the exterior with the exterior layer. So instead of doing this for all the mesh renderer, I just created a small script for the demo. And basically, I'm assigning different layers for the interior and the exterior. And then, for adaptive pro volume, I need to tell the system which layer to use. So let's use the interior and the exterior layer. And then I just need to bake again. So the setup is quite simple. Once you split your geometry between the interior and the exterior, you just need to assign the correct layer to the mesh renderers, and you don't need to assign any layer for the probes. So basically, at bake time, the probe will fire a lot of rays, and they will automatically find the layer they are the most close. So for example, the interior probes should hit a lot of mesh renderer with the interior layer, so they should be automatically assigned the interior layer, and that's the opposite for the exterior probes. So let's look at probe volumes. We can display the probes and look at the rendering layer mask. So automatically, those layers were assigned, and we can see that at bake time, we get two different areas just like this. We can look again at the debug probe sampling debug view. And now, if we select this pixel, since the mesh renderer is in the interior layer, it's only sampling the probe that are in the interior layer like this. And that's the opposite for the exterior meshes. So most of the leaking is gone, but we can still see a few issues here. So if we look at the debug view, we can see that those probes are red, like the system knows they should not be sampled, but they are still sampled, and that's because we are using the leak reduction mode performance. So the performance mode is trying to sample APV only once and pushing the sampling location away from the invalid probes, but sometimes it's not possible to find a perfect solution to sample all the valid probe and none of the invalid one. So with the quality sampling mode, you can sample APV up to 3 times, and you are sure that you will not sample any invalid probe. So this way, that's much better for the tent. And the quality mode has a slight performance override, especially on low-end mobile. So it really depends on your platform, but it should be fine for console or desktop. And if we look at the scene without the debug view, just like this, you can see that even if we can see some leaking with the performance mode, and it's better with the quality mode, it's still usable with the performance mode. So it really depends on your platform and if you absolutely need to avoid all the invalid probes. All right, so now that the scene is set up using ProVolume, and it's looking already quite great, let's take some time to compare light maps and APV. So this is APV, and this is light maps. So it's quite close, but we can see a few differences. Let's zoom in, and first, so APV and light maps. So if we look at under the table, we can see some indirect shadows with light maps, and it's much easier to get that kind of details with light maps. And sometimes it can be hard to capture, especially with 1 meter between probes with APV. So you will get just a bit more detail with light map for indirect shadowing. But if we look, so light maps and light probe groups, you can see that some of the objects, so for example, the plates and the glasses, they stand out a bit, and that's because they are lit with light probe groups. So it's a different solution. And with APV, we are using a unified solution for everything, so everything feels well integrated. So that's one advantage of APV, not having to rely on 2 solutions for lighting. And then if we look at the cliffs, so that's APV, and that's light maps, directional light maps, you can see that the directionality is much better with APV. So if you have a lot of normal maps or surfaces with facing a lot of directions, you will get better results with APV. And currently, we're seeing the indirect lighting debug view with APV and screen space ambient occlusion. So that's great to capture the detail, the high frequency detail that APV cannot capture. But let's look at how it looks without the SSAO. So if you cannot afford SSAO, maybe you can push a bit the resolution for APV. So for example, instead of 1 meter between probe for inside the tent, I used 30 centimeters between probes, so an additional subdivision level. And we go from 5 megabytes per scenario to 9 megabytes per scenario. And we can get back this indirect shadow under the table, so you get a bit more detail for your lighting. So if you cannot afford screen space effect like this, just push a bit IPV resolution. Now, let's just take a few moments to look at the performance. So on PS4, sampling light maps takes around 0.2 milliseconds. Sampling APV takes between 0.6 and 0.8 milliseconds. And on PS5, that's quite small for light maps, and between 0.1 and 0.2 milliseconds for APV. So APV is slower than light maps, but it's still quite effective while it's offering better directionality, a faster and unified workflow to avoid discrepancies in the scene. It uses less memory also, and we will see in a minute that it's offering also unique features if we want to increase the quality of our scene. David, up to you.
Yeah, thanks, Maxime. The scene's looking great. We're getting very clean results. But if I'm going to wear my art director hat just for a moment, I think it feels a bit static. And for that reason, let's explore some ways that we can add some dynamism to the scene. It's going to add some more visual interest. Our first consideration for any lighting artist wanting to add changeable global lighting to their scene would be sky occlusion. This is a technique where we try to spatially calculate the influence of the sky on points throughout the scene. Rather than just calculating direct visibility from a given probe and writing out a scalar, we actually allow indirect paths to the sky and store the results with some directionality. We do this by firing rays from all the probes in our APV system in the hope of finding some sky. Rays are fired in every direction from the probe, and the paths are allowed to bounce a certain number of times. After finding the sky, intensities can then be multiplied with albedo on each ray intersection, and then the sky influence is calculated for each probe in each direction. Using this information about the influence of the sky, we can do some really interesting things. For example, we can blend sky occlusion with sky color to create a plausible impression of sky lighting in even the deepest parts of the scene. As calculating the scene's ambient probe is cheap, we can do that part quite quickly at runtime, and this allows users to modify the sky during play, say for time of day or something like that. Then they can dynamically recalculate the ambient probe, and then when shading, combine this to give a convincing impression of changing skylight, which appears to bounce convincingly throughout the world. So Maxime, could you show us how to set that up?
Yes. So back to our scene. For this demo, I have a small script that is managing the sky, the lights, and all the environment settings. So basically, that's a dynamic sky. I'm using an asset from the asset store. It's the Azure Sky Dynamic Skybox for the sky. And currently, when scrolling the time, you can see that we still have the bake that is static. So let's clear lighting to see how it looks. So currently, that's a uniform color for the sky, and that's because it's using the settings here in the environment settings. Let's, for example, use a color, and you can modify the color that is coming from the sky. And that's something that we could animate for a time of day, so something quite bright for the day and quite dark for the night. So I did this with a gradient, and let's see how it looks. So that's already better, but the sky lighting is completely uniform. The color is applied everywhere, so that's not what we want. For example, for the inside of the tent, we should get some shadowing because the skylight should not affect the interior of the tent the same way that the exterior. So let's go into the lighting adaptive volume tab, and we can use the sky occlusion. So let's tune this like this. And then let's just reback to see what happens. So just to summarize, the sky occlusion is relying on two things, the ambient probe, and this one we can update at runtime, and it will define the color coming from the sky. And we also bake something static, so that's the intensity of the light coming from the sky. So you can think of it like white light coming from the sky and bouncing around in the scene. And that's quite useful if you want to have like occluded areas like the tent like this. And let's see how it looks now with the shadow. So that's much better than before. And basically, that's an easy way to add dynamism in the scene, since it's a single bake, so it's quite fast. And if you have a large world and you cannot afford a lot of bakes with a single one that's easy with sky occlusion, it's quite cheap. So, but the trade-off is that it's only managing the skylight. So, for example, in this scene, I switch the sun from mixed to real time, so we lose the bounce lighting from the sun, and we are only updating the sky lighting at runtime. So now that we saw how sky occlusion was working, let's turn to David to see if there are other ways to add dynamism in the scene.
Yeah, so another essential tool in the arsenal of the lighting artist wanting to inject complex lighting transitions into their scene would be lighting scenarios. Lighting scenarios are essentially empty slots or arrays into which you can bake probe lighting data. You might, for example, store some default lighting setup for the scene and then create a totally different aesthetic that you want to swap to based on some game event. For example, going from a daylit to a scene lit by candlelight at night. An important mention here is that you can actually bake and store multiple scenarios, and that means that scenarios have a critical advantage over sky occlusion in that you can store many more varied treatments with complex local lighting and not just the influence of the sky. As we allow multiple scenarios to be stored and blended, it's possible for users to create lighting keyframes. When used in combination with sequencing tools, such as Unity's timeline features, this allows multiple lighting elements to be coordinated at the same time. Remember, this can also apply to scenes which are not lit by the sky, such as indoor scenes with artificial lighting. And as mentioned at the start of this presentation, you may need to calculate and store probe positions and indirection textures for the whole APV structure, but you can have multiple scenarios sharing that same data, which is great optimization. Adding additional lighting scenarios is therefore a fairly low cost once you've paid that initial hit. So yeah, back over to you, Maxime.
Yep. So I just disabled sky occlusion and did a bake to get back to the state we had before. So no sky occlusion for this example. And I have another script, so it's the same mechanism. I can slide to through the time of day, and this time it's managing the light, but also the sky. It's blending between two cube map textures, so no dynamic sky, a texture for the day and a texture for the night. So let's see how we can use lighting scenario with APV. So if I go to the project settings, quality, DSRP asset, I can enable lighting scenario and lighting scenario blending like this. And then in the lighting window, we can see this new section lighting scenario that appeared. So for example, let's rename this scenario day. And let's just create a new one for the night. And then I can just set up my scene with the sky, the lights as I want, and I can bake again. So yeah, and the script is managing, as I said, the sky, the light, and the script is also managing the day and night, and you will see in a second that it's blending between those two scenarios. All right, nice. So now, just in a few clicks, we can blend between day and night, and that's, since everything is baked, that's quite cheap at runtime, as we saw on PS4 on the runtime performance slide. It's like 0.2 milliseconds for blending for the whole scene, so that's quite affordable if you want to do a time of day in your scene. All right, so everything is looking great for this scene. Now let's turn to Rémi to see if we can learn a bit more about lighting scenarios.
Thank you, Maxime. That was really looking great. So now that we know how to use scenario, let's try to use them in a more advanced example. And because we like a challenge, let's try to do a complex one. Let's try to do a day-night cycle, but with a real-time sky. And why a real-time sky? Like, for example, you would need, if you want to add volumetric cloud or something like that, you can't use a baked skybox as Maxime used.
And you say more complex. Can you tell us more why it's more complex than the thing that we did before?
Exactly. The thing is, what we did is just blending between one baked skybox with one baked scenarios to another baked skybox with one scenario. So basically, the lighting matched all the time. So it was kind of easy. But in our case, we will try to blend a real-time sky. So basically, that is updated every frame with multiple scenarios and try to blend them. So, and I'm not sure if it will go well. And on top of that, we really need to define how many scenarios should we have, where should we place them on the time of day, and how should we blend them as well. So in this example, for simplicity, we are using HDRP with a physically based sky, the real-time sky, and physically based light values. So as you can see, the sun will be 70,000 lux and the moon 1 instead of something much lower that we can use like in URP, for example. So first, let's talk about how many and where should we place the scenario. So to simplify, I started in the afternoon and ended up at around midnight or something. And for this, we are going to follow two simple rules. So the first one is, if the lighting changes, we are going to need another scenario. So let's place the scenario around each major color to see what that looks like. So here, each dot represents a scenario in our wheel.
And why is there some white and yellow dots?
Yeah, good question. Basically, when after the night have settled in, we switch some of the lamps inside the tent to be able to see something. And so this is what the yellow dot represents. Yellow dot means the light is on the tent. And our second rule is, the faster the change, the closer the scenario has to be. So for example, a light switching on is pretty fast. So that means we should add more scenarios. So let's adjust a little bit our scenario placement here. So that should look something like this, for example. And same after sunset, the lighting changes pretty fast. So we make them a little closer to have a better unified lighting, because otherwise indirect lighting won't match the direct lighting here. So in our example, like 8 scenarios seems about right. So now that they are placed, we just made a simple script to interpolate linearly between those scenarios and recorded a video of that. And we'll see that video. We would have loved to do that live, but we could afford to bake one scenario live, but not 8. You would have waited like 3 or 4 minutes. That's too long. So let's see what it looks like when we play it, and let's see if that's great or not. So as you can see, it's getting pretty weird after sunset. The lighting is kind of bouncing. So let's see if we can understand why and what did we do wrong basically here. So for that, let's go back to our sunset wheel. And in front of each scenario, I've added the sun elevation in degrees and the sun intensities as well. And as you can see, it starts from 70,000 to basically 0 after sunset, and then goes back to 1 at night because of the moon. So here there is 2 obvious takeaways. The first one is that there is a huge range of values. And the second one is that the rate at which the value change does not seem to be the same between the scenarios, as you can see, between afternoon and evening and sunset and twilight. So let's plot those on a graph to see if that's more clear. So the graph here confirms our intuition. The sun intensity is far from linear. And before the sunset, the intensity is changing maybe 1,000 of lux per frame. And after the sunset, it's more or less 10 lux per frame. So it's very different. So now let's add our indirect lighting intensity here and see if we can spot the problem. So basically, before the sunset, It does not seem to be the problem because the indirect lighting it's much lower than the direct lighting, than the sun. But after the sunset, it starts to be a problem because the indirect lighting intensity starts to be a significant fraction of the direct lighting here.
And so just to clarify, is the problem the indirect lighting or the technique that we are using?
No, the problem is not the indirect lighting at all. It's just that the sun is real time and the indirect lighting is baked. So we are basically in between scenarios. So before the sunset, the problem is more or less here, but then is hidden by the huge intensity of the sky. But if we go after sunset, then the indirect lighting starts to play a huge part in the lighting, and then we can still see the problem. So let's add our indirect lighting to our curve and see if we can spot the problem. So we can start to see what's happening. To blend our scenario, we made a super simple script to interpolate linearly between the indirect lighting scenarios. And when I say linearly, it means that we go straight from point A to point B, so from one scenario to another. And as we've seen before, our direct lighting is far from linear. So what happened is that there is a mismatch between our direct lighting and indirect lighting. And it's a problem. And it's a problem basically because of exposure. And to understand exposure, let's try to look at this specific frame, so basically after the sun has set, to understand why. So here's that frame. We can see it's divided in two parts. The first one is the sky, which is lit by direct lighting and updated in real time. And when I say lit by direct lighting, it means that the rays start from the sun and go lit the sky directly. It does not bounce. And then you have the ground that is lit by indirect lighting. So that means the rays goes from the sun, then bounces on the sky, and then try to lit the ground because the sun has already set and is already behind the dune. And this is baked, so it's blended between scenario here. So here we have two versions of the same frame. On the left, we basically have the proper exposure for the sky, which is lit by direct lighting, but then the ground gets overexposed. It's too bright. And then on the right, you can see the exposure is set up for the ground, so the ground is looking great, but then the sky is underexposed, meaning it's too dark. So in an ideal world, we want to have multiple exposure for the same frame, but that's not how it works. We need to only expose our frame once. So let's try to reconcile our direct and indirect lighting. And in addition, since our intensities vary a lot during the day-night cycle, as you've seen, we start from 70,000 to 0, we need something called automatic exposure. And automatic exposure is just, simply put, the engine will try to guess the proper exposure based on what it sees on screen. So it's simple as that. So when there is a mismatch, like here, basically automatic exposure tries to guess the proper exposure, and sometimes it guesses for the ground, sometimes it guesses for the sky. And then since it's updated every frame, it tries to adjust and tries to autocorrect, leading to the bounces we've seen in the first example. So here I've added the real-time exposure to what happened on the first example. And as you can see, it tries to autocorrect, and instead of going down and going back to something closer to the sun intensities, goes back and up, and then starts to adjust. So here, what can we do to make things better? So the first naive solution would be to just have more scenario. It would sort of work because the indirect lighting and the direct lighting would basically match more. But then there is many problems with that solution. The first one is that it will take more time to bake, even though EPV is fast, like baking a 15 scenario is too much. It would take more size on disk. It becomes really tedious to place, and it's not really flexible. If you have to move your sunset time, for example, you need to move all your scenarios one by one, and that's not something we really want. And if you zoom in between scenarios, you can still see the mismatch, so it's not a perfect solution. So basically here, what we want is try to make the blue curve match the red curve here. And one solution would be to try and retrieve the blending rate of the sun directly. So let's see if we can find a way to do that. So one solution would be when we bake our scenario, we can store the sun intensity directly in the scenario. So for example, after sunset, it would be more or less 2000 lux. And after twilight, it's more or less 0 lux. And then when we blend, so for example, here at the middle, we can check the current sun intensity and guess exactly where we should be on the curve. So here, for example, if we ask the sun how bright it is, it says 50 lux or something. So that means instead of being at around 50% in the middle as we expect, it means we are closer to 75% of blending. So we can use that percentage for our indirect lighting to be able to get closer. So for example, here, it's supposed to be 200 lux for indirect lighting. But if we use this weighted blending and do not go 50% and go 70% on the blending, it's more or less 50 lux. And as you can see, now both of our curve matches. So let's adjust our little script that we made interpolating linearly to basically use that weighted blending now and see how it goes. So as you can see, it's already much better, but it's not perfect. I don't know if you saw, but let's watch that again to be sure. I don't know if you saw, but right after sunset, you can see the lighting goes up a little, way less than before, but there's still some things to do to make it a bit better. And let's watch that, that example with the exposure to make sure it's clear what happened. So it goes down, and then the exposure goes up a little and then goes down. So as you can see, the curve is much smoother than it was before, but we still need to get rid of that little bounce. So let's see if we can do better. So let's go back to our sunset wheel here, and instead of the intensity this time, now that we understand exposure, I've added the exposure and the resulting multiplier we use in code. And we need this multiplier because we are in a game engine. And basically, this is to convert the huge intensity that are used by the sun to be able to display that range into a lower screen dynamic range. So for example, in the afternoon, the luminosity is huge. As you've seen, it's 70,000 lux. So we need a really tiny multiplier on the top. But at night, there is very little luminosity, so we can have a much larger multiplier. So basically, we need to compress that huge range of intensity, because we are using physically based light units, into something smaller to be able to display it on the screen. So what can we learn from this? So even though the value are super tiny, the range is still huge. So the same thing as our intensities. And given such low values, if the exposure is not perfect, it can result in drastic change in lighting. And that's what we've seen on the previous video. But as we've seen as well, the automatic exposure is not jumping from one exposure to the next. It's basically interpolating, and it has a speed. So that means in between scenarios, most of the time, the exposure won't be perfect. And it will have trouble adjusting properly, and it will lead to the small bounces that we have. And basically, we'll have trouble adjusting. So what can we do here? So from the beginning, our problem seemed to be that we travel through a large range of value, whether that is for exposure or for the intensities. And the value that we used were the actual value of an afternoon sun. This is why we call that physically based light unit. But there is nothing preventing us to use lower value to try to reduce that range. So let's see if we can do that. So here we can decide to divide all those intensity by an arbitrary number. So here what I did is just basically selected all the light of the scene and divided by 30. I chose 30, but I could have chosen any other number, for example, 10 or 50, just about something that felt right. And it won't be a real life value, but if you adjust your intensity and then you adjust your maximum exposure, then the result should be the same. So before our range was about like 70,000 lux, now it's more or less 2,000. And our maximum exposure was like 14, and now it's more or less 7. So the range of intensity is reduced, and the range of exposure is reduced as well. And basically, by making the range smaller, we are making automatic exposure job easier. So let's watch that version, and this time it should be much more forgiving. So as you can see, there's little to no bounce after. And then let's watch the same video with the exposure curve. And you can see it start lower and then starts to go down. And then it's much smoother. You have a little bump because of the light coming up here. But then this is actually what we wanted from the beginning. But I can already hear one question coming up.
Yeah, when should we use realistic light values or not? It seems like trouble in this example, so... Exactly,
that's a really good question. Basically, it's perfectly correct to use physically based value, and for multiple reasons. For one, it's easier to set up because we have reference value. That means we are not eyeballing everything. Like, for example, when I did the first try, I know that the sun is 70,000 lux in my case, so I just need to put that and no question asked. Since we are using like proper equation and proper units, the result would be more accurate for post-processing, for example, and you'd get more realistic results. And it will ensure also consistency across the scene. Like, for example, in the non-PBR example, I chose to divide by 30, but then if another artist, for example, did the same on their scene and divide by 10 or 50 or another number, then the lighting between those scenes won't match, and then there will be trouble if we try to blend those scenes. So it's easier for all of those reasons. But using non-physically based value is also valid as long as you know what you're doing. For example, for gameplay reasons, if you want to avoid glare, by looking outside a window to see your opponent, for example, that's something that would happen with a huge intensity of value. So that's basically more complicated. So for gameplay reason, it could mean a lot. For artistic reason, it's much simpler to fine-tune the look of your game if you are using non-physically based value. Or for even rendering reason, like here, we are making like basically the worst case scenario, a time lapse of a sunset with huge values. So to simplify our exposure job, we just reduce that range and make that more correct, basically. So here the key takeaway would be, and this is something we touch all along the presentation, basically between the dichotomy between the light probe groups and APV, between sky occlusion and lighting scenario, or even between the performance mode and quality mode. Basically, there's no perfect solution. There's just only choices that you have to make depending on your budget, on your context and your project, etc., etc. And before we go, if you want to learn more, here, don't forget there is tons of information about those in the URP and HDRP ebooks that's behind this wonderful QR code. And lastly, the next talk is this stage is a great add-on to what we talked about. They will basically start from this Oasis scene, and they will set everything on fire. They will add gameplay, they will add fancy shader, etc., etc. And they will also do most of this live, so it's really interesting. So I encourage you to stay to continue learning about this. Thank you very much.